So we're still talking about the harmonic oscillator problem in quantum mechanics, and we moved on now to talking about it in terms of an energy basis in the Heisenberg-Dirac approach. So what we have now is our lowering operator and our raising operator. Where what we've done is to first write out our Hamiltonian, dimensionless Hamiltonian, as A dagger A plus 1/2. So we're going to use the Hamiltonian to raise up and lower the state. And where I left off last time was that if we apply, say, the Hamiltonian to a reduced energy state, and say we start at the ground state, then that's going to give us 1/2 the energy in the ground state. Or basically the eigenvalue is the Hamiltonian, the eigenvalue, the energy, reduced energy is 1/2, ground state energy is 1/2 times h bar omega. And now if we apply a raising operator to this energy, this ground state, so we apply, let me say that again. If we then operate with A prime on our ground state, then what we should get is the rest of the energies, where n is 0, 1, 2, dot, dot, dot. Or we can write out the energies of all the states, n plus 1/2 times h bar omega. So that's kind of our goal. That's what we're working toward, is to try and get all those energies to kind of prove that, you know, if we're in the third energy level, then we should be able to get this energy of 3 plus 1/2 times h bar omega. But the first thing we need to do is to try and figure out what these coefficients, or these normalization coefficients, for the raising and lowering operators. So I'm going to change now. Instead of writing the energy operator this way, I'm going to change to a much more, a much easier notation, just n. So n stands for the nth energy level, and it'll save us a lot of time in writing things down. So if I apply a lowering operator to n, the n state, then I'll get my coefficient c sub n, and then I'll reduce the state to the n minus 1 energy level. Similarly, if you were to apply to the nth bra, the adjoint, or basically the version of the complex conjugate, that should also lower things down. And we're giving us the complex conjugate of the coefficient. So basically you can either lower the ket state, or you can lower the bra state. But to lower the bra state, you have to take the complex conjugate of the operator, which is basically, in this case, taking the adjoint of the operator. So what we have is, if we apply A dagger A, and we take the product between the states n, what we're basically doing is lowering this side. So that's Cn n minus 1, and we're lowering this side, Cn star, those coefficients as numbers, so you can take them out front. So you get Cn star, Cn, n minus 1 product with n minus 1. Now that's basic, and we'll write this now as the norm squared n minus 1, n minus 1. So now if you remember, A dagger A is also the dimensionless Hamiltonian minus 1/2. So that's kind of like taking the same thing as saying, let's take the product operating with the Hamiltonian minus 1/2 on these states n. And that should be equal to Cn squared. Okay, so I can break this up. So I have n, the Hamiltonian, so the inner product of the Hamiltonian operating on n minus 1/2 n n is equal to Cn quantity squared. Now I said that taking the Hamiltonian and operating on a state n gives me n plus 1/2 with the state back again. So that's basically the eigenvalue problem to get the total energy. So if that's the case, then I get n plus 1/2 times the inner product of n with itself minus 1/2. The inner product of n with itself is equal to the norm of Cn squared. So the 1/2s cancel. So I basically get n times the inner product of n with itself. The rest of these cancel, so we don't worry about the 1/2 anymore. So therefore, I'm left with n, the inner product of n, is equal to Cn squared. Now, since these states have been normalized, then this equals 1. And what we're left with then is Cn quantity squared is equal to n. So in a general form, I basically write out that Cn is equal to the square root of n times e to the I phi. So I have to write it out that way because there could be a complex nature to Cn, but in this case, the phi is an overall phase factor for the wave function. So therefore, I'm interpreting the e to the I phi as a way of saying that not only can I operate on the state and change its energy, but I could also rotate or shift the phase of the wave function. The wave function is still the same. This is just a shift in the wave function. And so it doesn't affect the energy of the problem at all. It just means that, you know, the wave function can be out of phase. If I have a standing wave, I can shift it by 90 degrees, 30 degrees, you know, 270 degrees. Now, of course, when I take the complex conjugate of Cn, multiply with Cn, then this factor disappears, and I just get n squared. So in the end, that phase factor doesn't really modify the problem at all. It just says that nature allows us to shift the wave function if we want to. We can move it inside its plane, and we still get the same. So in this case, I'm going to kind of take the easy way out and say that, let's say that this is just equal to, the phase is equal to 0. We don't have a phase shifted wave function. If you want to deal with phase shifted wave functions, then you have to really move on into something called quantum field theory, where then you apply it and it has different consequences. But in this case, we're really worried more about the energy levels, not too much the shape of the wave function. And so we're just going to take that phase out of it. So in the end, what we get is that if I apply a lowering operator to a state, then I will get a normalization of the square root of n, and then the energy level 1 down, right here. Similarly, if I was to apply the raising operator on a ket, we could run through the entire procedure again, and if I did, this time what I would find is a normalization factor of n plus 1, and now I've raised up the state by 1 value. For the lowering, the normalization is the square root of n. For the raising, the normalization is the square root of 1 plus n. So now, what if I apply this thing that's related to the Hamiltonian to our state n? So now there's a two-step operation. Well, the first one is just going to give me the square root of n, and then I have the raising operator, but I've lowered down the state to n minus 1. And now if I apply a raising to n minus 1, I get the square root of the state n minus 1 raised up 1, and then I raise the state up 1, like so. So I get the square root of n times the square root of n, and I get the state n back again. So I get now a normalization, or I should say, sorry, an eigenvalue of n squared times the state n. So we could probably write this thing as the number operator, capital N, where we're basically pulling out the squared of the state without actually modifying the state. So if you notice, this is an eigenvalue problem where we have the same final state right here as the initial state right here, with an eigenvalue of n squared. So therefore, our dimensionless Hamiltonian, we can write as the number operator plus 1/2. So, I mean, we haven't really changed anything much, but what we've shown now is that the eigenvalue of the number operator is n squared.